Hi, I'm Steve Reising, a professor at Colorado State University in Fort Collins, Colorado. I'd like to speak with you about TEMPEST-based CubeSat microwave sounder constellation to improve revisit times of LEO satellites for weather forecasting. I'm the PI for TEMPEST-D, working with Berg and Professors Chandra and Kummerow at Colorado State University. We are leading the science and validation for the TEMPEST-D mission. JPL has provided the instrument, is responsible for its calibration, led by project manager Todd Gaier pre-launch and Shannon Brown post-launch. The instrument manager is Sharmila Padmanabhan. Our partner on the spacecraft is Blue Canyon Technologies in Boulder, Colorado. So here are three images of Hurricane Lorenzo in the 2019 hurricane season. And if I tell you that two of them came from operational satellites and one from a CubeSat, can you tell me which one is which? Well, if you guessed the middle one being from a CubeSat, you're correct. The left and right ones are from operational instruments AMSR-2 and SSMIS, respectively, and the middle one is from the TEMPEST-D CubeSat. A little more about TEMPEST-D. If we compare with the state-of-the-art operational sounder operated by NOAA called the Advanced Technology Microwave Sounder, or ATMS. Shown here in the yellow circle, it has 75 kilograms of mass, takes 100 watts of power, and shown here integrated on the NPP satellite in Boulder, Colorado. The sensor is built by Northrop Grumman, integrated by Ball. TEMPEST-D CubeSat is about 20 times smaller in terms of mass and power consumption than ATMS. It's 4U of a 6U spacecraft. And here's the entire 6U TEMPEST-D spacecraft, 34 by 20 by 10 centimeters, less than 12 kilograms. And the XB-1 produced by Blue Canyon Technologies is shown here at the top. And the solar panels deployed on a bench at Blue Canyon Technologies in Boulder. So the TEMPEST mission is called the Temporal Experiment for Storms and Tropical Systems. The TEMPEST addresses the 2017 National Academy's Earth Science Decadal Survey, one of the most important science questions. Why do convective storms, heavy precipitation, and clouds occur exactly when and where they do? So to approach that question, we proposed in 2013 to the NASA Earth Venture Instrument opportunity a constellation of 5 identical 6U CubeSats to substantially increase the temporal resolution of clouds and humidity observations and of severe storms observations for up to every 5 minutes for up to 30 minutes. We were chosen as a NASA Earth Venture Tech Demo mission for 90 days, and we delivered a 6U CubeSat with a 5-channel millimeter wave radiometer ready for launch less than 2 years after our PDR. Then we were launched by Orbital ATK from NASA Wallops to ISS in May 2018 and deployed into orbit about 2 months later. So there's an additional TEMPEST flight instrument that was made at the same time as the TEMPEST-D instrument to be deployed on board ISS in December 2021 for 3 years to yield global near real-time brightest temperature data. So right out of the box, our first few orbits on September 11th, 2018 measured hurricanes. So during the 2018 hurricane season, we observed first on that first day Hurricane Florence, which later made landfall in North Carolina, and Hurricane Helene, as well as others, such as this one here. So comparing with the NOAA GOES geostationary imagery, here we see the visible imagery of Hurricanes Florence and Helene, and we know that this imagery is available with high temporal resolution, but it just observes the cold cloud tops in infrared and doesn't peer into the storm as the millimeter wave sensors do, where we see the details of the rain band here shown in color and the ice ice scattering, and so on, where the precipitation is really formed in the storm. So later in the 2019 hurricane season, our TEMPEST-D observed Hurricane Dorian over a 10-day period, every day. And so we formed the hurricane track just from looking at TEMPEST-D observations alone. The millimeter wave brightness temperatures penetrate to different depths in the atmosphere as they move off the 183 gigahertz water vapor absorption line, as shown in the animation here in the lower left. So our TEMPEST-D CubeSat has operated for more than 2 years, 9 months on orbit to performing global science quality observations. And we met all our level 1 requirements within our first 90 days of operations, demonstrating TRL-9. Our sensor is well calibrated, highly stable, low noise, with performance rivaling that of operational satellite sensors. And we're producing atmospheric science data, especially in correlation with other satellite sensors and ground-based polarimetric radar networks. So the TEMPEST-D brightness temperatures are shown here on a global basis at 87 gigahertz, our lowest frequency, all the way up to 181 gigahertz, our highest frequency. So these are performed the first few months of the mission, and these were performed last summer in July of 20. So the TEMPEST-D instrument performs end-to-end radiometric calibration by observing two known brightness temperatures. One is cold sky or cosmic background of 2.7 Kelvin, and another one is the calibration target produced by Zach's millimeter wave, measuring its temperature that is also monitored on orbit continuously. And we scan across the Earth scene at plus or minus 60 degrees from nadir, and the two calibration points and the Earth scene are shown here. So our spatial resolution ranges from about 12 kilometers at our highest frequency to 25 kilometers at our lowest frequency of observation. So our radiometer has been extremely stable over the mission to date, as shown here by the noise produced by the radiometer. It's actually very low noise due to the Northrop Grumman and JPL indium phosphide HEMT amplifier technology, the process that has been developed and optimized for this, in part from funding from the NASA's Earth Science Technology Office. So this reduces the risk for future operational sensors and demonstrates the high stability, as well as improved performance when we compare the ATMS noise level with TEMPEST-D. When we compare apples to apples with same integration time and bandwidths, we find that TEMPEST-D has a factor of 2 lower noise in 4 out of 5 channels. And this is all documented in a paper led by Sharmila Padmanabhan of JPL. So in order to validate our sensor, we compared it with the Global Precipitation Mission's GMI radiometer and 4 microwave humidity sounders on NOAA and ESA EUMETSAT satellites. Our absolute calibration is within 1 Kelvin, precision within 0.6 Kelvin, meaning that our radiometer is very well calibrated and highly stable with very low noise, with performance rivaling that of much larger operational instruments. And here we're showing tracking Hurricane Dorian, comparing TEMPEST-D with the Global Precipitation Mission by NASA and JAXA. Our TEMPEST-D data is publicly available. It's been downloaded by 32 institutions in 9 countries on 4 continents. And we have studied the calibration errors and show no evidence associated with changes in instrument temperature. And you can see the paper led by Berg of Colorado State University. So when we take a look at a few detailed observations, one of them is with Hurricane Laura in the 2020 hurricane season. It tied the historical record for landfall wind speed in Louisiana, and unfortunately it destroyed the weather radar where these observations are taken. here, and this is before and after picture. That's in Lake Charles, Louisiana. So TEMPEST-D made measurements just 3.5 hours here before. Global Precipitation mission flew over, and we showed these measurements are very comparable, even though they were at different times. The spatial resolution is higher with GPM, and the scan angles are different because the scanning configuration is different, and also the satellite track is different. But the observations show very good comparison, as well as 8 hours later here, where we observed Hurricane Laura 1.5 hours after dual precipitation mission did. So our TEMPEST-based microwave sounder, if we look to the future for constellations, we take the 5 channels for moisture sounding, as well as 7 additional channels based on the tropics channel design, with weighting functions shown here in terms of sensitivity to the temperature with altitude, and here the weighting functions are for water vapor for the TEMPEST-D channels. So we performed simulations of the TEMPEST-based microwave sounder in CubeSat constellations at 830 kilometers altitude, which is the altitude of the current operational polar orbiters from NOAA and ESA EUMETSAT, NOAA 20 and METOP-C. So we're calling these CP, the current polar orbiters. If we add to those current polar orbiters a configuration of TEMPEST-9, which means 3 in each of 3 orbital planes at inclinations of 30, 50, and 70 degrees orbit, plus the current polar orbiters. That's one. Another one is moving all of those up to polar orbit in 3 different orbital planes and keeping CP. And then the last configuration is, what if CP was not used, but instead we added 3 TEMPEST polar orbiting CubeSats to the TEMPEST-9 constellation. So we compared the performance on equal metrics of all of these. And what we found was the mean revisit time, or mean time between subsequent observations for these constellations. The current polar orbiters, 2 satellites, give 6 to 7 hours of mean time between revisits. TEMPEST-9 at the 3 inclinations, added to the current polar orbiters, reduced that to 1 hour or less, mean time between subsequent observations. When we move the 9 TEMPEST up to polar orbit, it gets a little longer, closer to 1.5 hours between subsequent observations. And then TEMPEST-12, where we take TEMPEST-9 and replace the current polar orbiters in our constellation with 3 TEMPEST polar orbiting satellites. And that has similar performance to TEMPEST-9 and CP. So we can compare with another statistic, the median revisit time. The current polar orbiters are 6 to 7 hours, and the red TEMPEST-9 plus CP reduces that time to 1.5 hours, nearly globally, nearly at all latitudes. Then ECMWF forecast nature runs were used for water vapor and temperature at 700 millibars pressure altitude to compare the sampling error of the current polar orbiters, shown in blue, to that of several other configurations that reduced that error by a factor of 2 at most latitudes and had similar performance for temperature, as shown on the right. So in conclusion, the CubeSat microwave radiometer, called TEMPEST-D, has successfully demonstrated global measurements of moisture, cloud liquid water, and ice water in more than 2 years and 9 months on orbit to date. We performed quantitative comparisons with the Global Precipitation Mission microwave imager and microwave humidity sounder satellites on NOAA and METOP satellites, demonstrating that our accuracy and precision are comparable to those of much larger satellites. Our radiometers are highly stable over the mission to date, with no evidence of calibration errors over temperature. And we have a very well calibrated and highly stable radiometer with very low noise. And industry is set and ready to produce the constellations over low-cost, rapid schedule for production deployment as well as operation for a Tempest-based constellation. So adding a 9-satellite constellation or more to polar orbiting satellites would improve revisit time of moisture and temperature sounding of NOAA and METOP satellites from 6 to 7 hours to 1 or 1.5 hours nearly globally. Thank you very much.